In this, our third lab, we're going to be working with a package, ggplot2, that's used to visualize data. And here we have a list of some of the topics that we're going to be covering. The organizing principle that we're going to use in this lab when we're talking about data visualization is this concept of a geome. And we'll begin with examining a particular geome point, that's used to make scatter plots. Then we'll move on to geome line that's used to make line plots. And then we'll address some miscellaneous topics. Every time you load up and install that third-party package, ggplot2, you will have available to you the data frame MPG that we use quite frequently in this course. And so just as a reminder, here are some of the variables in MPG: 15 different manufacturers, 38 different models, displacement the size of the engine, the year in which the vehicle was built, the number of cylinders it has, the type of drive, four-wheel, front-wheel, rear-wheel drive, city and highway mileage, and the type of fuel. And down here we have this that I've referenced several times before, the idea that each one of these variables has a characteristic. It either is part of this group or it's part of that group. And what really matters is not whether we think a particular variable is discrete or continuous, but what R thinks about whether or not a variable is discrete or continuous. And a good example of that are these two variables, year and cylinder. So when we think about the variable year, it has only two levels, 1999 and 2008. R considers that to be a continuous variable. But goodness, with only two levels, we probably are going to think of it as discrete. Similarly, cylinder. Cylinder has only 4, 5, 6, or 8 cylinder engines. We will probably want to consider cylinder to be discrete rather than continuous and INT. So what I'm going to do is I'm just going to jump right in to this concept of making plots using the package ggplot2. And as a consequence of just jumping right in, there may be some initial confusion. Don't panic. Eventually, it will all become clear, I hope. So what we have here is a very simple scatter plot with highway mileage on the y-axis and city mileage on the x-axis. And here we have the code that would make that plot. And the code consists of a couple of components. The first component is the plotting function. And the plotting function begins, and remember, anything that's in Courier, you always do exactly like that because it's an R keyword. So we've got the keyword ggplot, and that tells R make a plot. And then we've got this data equal that points us to MPG, the data we're going to use to make the plot. And then we're going to add as a layer. We're going to see that ggplot2 is a layered language. We're going to add as a layer this thing that's a geome. And it's a particular type of geome. It's a geome point. And a geome point is going to make a scatter plot. And there's some additional information here that tells us what goes on the x and y axes. There's a note here in this little rectangle, this little box, that says if you actually use this code, you wouldn't get exactly this plot. And the reason is that I did some additional formatting that I haven't shown the code for because I thought it might be a distraction. In any event, there's an awful lot that's going on in this slide, but really the take-home message is that in order to make a plot, such as the one we see here, we need two things. We need the plotting function in the form of ggplot that says make a plot, and then added to it as a layer, we need a geome, and those two things are connected by a plus sign. I could have written all this code as a single line. I wrote it as two lines. Plus sign at the end tells R to continue reading on to the second line. So, the organizing principle of this lab lecture is the concept of a geome. There are many geomes, and all the geomes have this particular format. But the obvious question is, well, what the heck is a geome? Well, geome actually refers to just the type of symbol that you're going to see in the plot. So here's a list of the geomes we're going to consider in this lab, and we can think about the kind of plots that they make. Geome point makes a scatter plot. Geome line makes a line plot. Geome column makes a column plot. Geome histogram makes a histogram. Geome box plot makes a box plot, etc. In the appendix, there's a whole bunch that are discussed, and there are many others that we're simply not going to have time to go over. So, as I said earlier, I went through the lab and I identified the slides that I considered really important, and this is the second of those really important slides because it shows the template that we're going to use when we present information on geomes. So on the previous slide, there's going to be two things. There's going to be the plotting function in the form of ggplot2, and there it is. And then we're going to add as a layer, the geome. Now, there's a bunch of code here relative to our geome that I could have put in one long line, but I put in a bunch of separate lines separated by commas because the point I'm trying to make is that every geome has 5 components. So every geome has 5 components. The first component is every geome needs to have some indication of what the data is that it's going to operate on. It needs to have this rather strange thing called an aesthetic mapping that I'll go into more detail later. It has options, it has stat, and it has position. So every geome has those 5 components. Now that may seem a bit odd because a couple of slides ago, I was able to make a dandy little plot, rather simple plot, with just this code, and clearly we don't see all 5 of those components present in this code. So what's going on? What's going on is that although every geome is going to have these 5 things, they don't necessarily need to be specified. So for example, consider the data. I don't need to specify the data. It doesn't need to be specified even though it's required because the data will be inherited from MPG. If I'm going to make a scatter plot, for sure I'm going to have to tell it what the X and Y variables are. Those are going to be required. The third component are the options. And the whole concept of options is that they're optional. So they're not going to need to be specified. And the fourth component, stat and position, those fourth and fifth components, they're going to be required, but every geome comes with its defaults. If the defaults are adequate, they're not going to be specified. So, although every geome is going to have these 5 components somewhere, they don't all need to be specified because they can either be inherited, they can be options, or they may have defaults that are just fine. So now I want to talk about this idea about inheritance that I just mentioned. This code here is typically the way we're going to do business. We'll have our plotting function, and inside that we will specify the data frame that we want to use. And we'll add to that a geome. If we want to make a scatter plot, we'll add geome point. If we want to make a line plot, we'll add geome line, etc. And inside that, we'll provide whatever additional information is needed to make the plot. So this is typically the way we do business. What we'll see in several instances in this lab is an alternative approach, and I'll discuss why that would be when we get there, where we take all the information. All the information is contained within the plotting function. It's all inherited by geome point, and therefore nothing is required. And rarely we'll see scenarios like this, where nothing is specified in the plotting function and everything is specified within the geome. But for the most part, this is what we'll be doing. Just kind of as a reminder, there's a difference between this piping operator that we saw in the previous lab and the plus sign that we're seeing in this lab. They're both used to join one line to another, but their roles are slightly different. So the piping operator is associated with a particular package, dplyr. And every time you see the piping operator, you should think and then. The plus sign. The plus sign is associated with a different package that you install and load ggplot2, and it's used to add layers. So that's the distinction between those two guys that you often see at the end of lines. So, just as a review, in order to make a plot, you need these two things. You need the plotting function, you need the geome, and they should be connected by a plus sign. And every geome has these 5 components: the data, the strange thing called aesthetic mapping, the options, the stat, and position, but they may not need to be specified necessarily because they can be inherited, exist as defaults, be optional. And typically what we do is we specify the data within the plotting function, and everything else goes within the geome. So, this rather odd duck AES. What's it doing? So again, if we think about our template, we've got our plotting function, we add as a layer, our geome, and within our geome, we've got this AES business. What's it doing? So, here we've got a simple scatter plot with highway on the y-axis and city mileage on the x-axis. And let's look at this little point right here. A little dot in that position. That little dot has a number of features or characteristics. You can call them aesthetics, call it what you want. So what are some of those features or aesthetics? Well, the first feature aesthetic is that relative to the y-axis, it has a location of 20. And its location relative to the x-axis is 15. And if I look at that little point, I can see it's got a shape. It's a dot. It has a color. It's black. And it has a particular size. So what's this AES all about? What is this aesthetic mapping all about? Well, we see it coded in like this. You see it coded in like this. So aesthetic mappings are specified within AES. And so all this stuff here goes within the open and closed parenthesis of our geome. So you always see code that looks like this. But what's it actually doing? What's it doing is it's causing R to evaluate each and every record and doing an appropriate mapping. Or another way to look at it, it's taking what's in the data frame and converting it something in the mind of R that can then be plotted out. So for this particular case, if we map the X aesthetic onto the variable city mileage and the Y aesthetic onto the variable highway, then every one of these records is going to be evaluated, and the value of city mileage is going to determine the X location, and the value of highway mileage is going to determine the Y location. A couple of points down here. I use the word location rather than position because location refers to its location vis-a-vis the X and Y axis. Position is one of those 5 components: the data, the aesthetic mapping, the option, the stat, and then the position associated with every geome. And down here, kind of a fine point, technically you speak of aesthetics being mapped to variables instead of the other way around, but oftentimes my terminology gets a bit sloppy. So let's look at some aesthetic mappings in a very simple case. We're going to start off with a very simple data frame called MPGA. There's our plotting function. We specify our data frame. Data equals MPGA. We add as a plus sign our geome. We want a scatter plot, so we use geome point. There are its opening and closing parentheses. And inside that, we have our aesthetic mapping, which has its own opening and closing parenthesis. And so we've mapped X location on the city mileage and the Y location on the highway mileage. So every one of these records is evaluated, and the value of city mileage determines the X location, and the value of highway mileage determines the Y location. So what have we seen so far is the aesthetic mapping has its own parentheses, and aesthetic mapping is nested within the parentheses of geome point. Every record is evaluated, and the value of the record determines the value of the particular aesthetic or characteristic. And what we've seen so far is a scatter plot, where we've mapped X on one variable and Y onto another variable, but there are other aesthetic mappings that are possible. We can map shapes and sizes, colors and fills, and that's what we're going to look at now. So we'll begin with this idea of shapes, colors, and fills. And so we're thinking about what's available to us when we're making a scatter plot with GeoPoint. And we have a series of markers, possible markers that are available to us, a bunch of different shapes that are available to us, and they're shown here. And they kind of come in three different clusters. Those three different clusters are shown in this table. We've got 0 to 14, like this. And they're essentially lines. So you could have a line like this. And if you want to determine the color of those lines, you'd use the word color. And then you've got a bunch of solid shapes, 15 to 20, like that. So if you had a solid shape, you specify the color by the word color. And then you've got these guys here that have got a little square here. And it's got something on the inside of it. And the terminology here is a bit tricky. We're going to use the word fill to refer to the predominant color on the inside of the marker, and the word color just refers to the border. So that's what is being said here. So we previously did the aesthetic mapping of location. Now we're going to aesthetically map shape. We're going to use this data frame MPGA specified within our plotting function. We add a layer, GeoPoint to get a scatter plot, open and close parenthesis of GeoPoint, open and close parenthesis of the aesthetic mapping. So we're doing three aesthetic mapping. We're putting the X location associated with the city mileage, the Y location associated with highway, but now, as an additional feature, we're mapping shape onto drive. So what's R going to do? R is going to evaluate each one of these records. And it's going to look at those records and say there's 1, 2, 3 different shapes. So when I map shape on the drive, as each one of these records is evaluated, the shape of the marker is going to be determined by the drive. So in this particular case, what's going to happen is the front wheel drives, we get triangles, the four-wheel drives, we get circles, the rear wheel drives, we get squares, and I'll get a nice little legend telling me how that aesthetic mapping is operating. I can also aesthetically map size. So, specify a slightly different data frame. Inside of our aesthetic mapping, we're mapping X and Y location on a city and highway mileage, but now we're mapping size onto displacement. So we're mapping size onto displacement, so each one of these records is going to be evaluated, and the value of the variable displacement is going to determine the size of the marker. So when this particular record is read, you can see it's got a very small displacement, so the size of the point is fairly small. When this particular record is read, it's got a fairly large displacement, so the size of this marker is fairly large. So this is the code that we just saw, and this is the plot that we just saw. And we might look at this plot, and we might see that little point, and it looks terribly tiny. We're not really sure whether it's a point or whether it's just an imperfection on our monitor. So what we might want to do is increase the absolute size, but maintain the relative size of the markers. Here's some code that we can add as a layer to do that. And as always, anything that's in Courier, you replicate exactly as shown. The only thing that you can change are these two numbers, and these two numbers control the minimum and maximum size of the marker. So we started off with our original code, these first two lines, and then, as we'll see over and over again, ggplot2 is a layered language. We're going to add as a layer this next line of code that specifies I want the minimum and maximum size of the markers to be this. By doing this particular operation, I'm able to increase the absolute size of the markers while maintaining their relative size. And as often is the case, we come back to this idea that all these variables are going to fall into one of those two categories, and it really matters. So if we think of what's happening in this particular line of code, I'm mapping size onto a variable. When you think about size, size is something that's continuous. And so it makes sense that we map size onto a variable. That variable should be a continuous variable. And if we come up and look at displacement, yep, it's a noon. It's a continuous variable. In contrast, if we think about shape, shapes are discrete. Triangles, diamonds, squares. And so it would make sense to map shape onto a discrete variable such as drive. We come up and look at drive, you can see that it's a character, it's a discrete variable. Now, what's really cool is that when it comes to color, we can map that onto either a discrete or a continuous variable. Both will work, the output will differ. So in this case, I've mapped color onto drive. Drive is discrete, 3 different drives, 3 different colors. Here I've mapped color onto displacement. Displacement is continuous, so I get a continuum of colors and a legend that reflects that gradient. The third really important slide is shown here. And it makes the distinction between setting and mapping. And so there's a bunch of code here, and this bunch of code actually wouldn't run. What we're saying here is that you should either do this or do that. Don't do both. But I just wanted to present the code in this particular format to help make the distinction between setting and mapping. So let's think about mapping first. So a quick review of mapping. So this is a mapping right here. So the mapping is preceded by AES, and there is the open and the close parenthesis of AES. And in this particular case, what I've done is I've mapped color onto drive. So the aesthetic color is associated with a variable. It's associated with a variable drive. And what's going to happen is every record is going to be evaluated, and the value of drive will determine the color of the marker. And since there are 3 drives, when we look at our plot, there will be 3 different colors. So that's aesthetic mapping. The setting, there's our comma, there's our setting. That's occurring right here. That's occurring in the position that we reserved for an option. So setting is actually an option. Now we're associating color, not with a variable. We're not associating with a variable, but we're associating with a particular value in quotation marks, the word red. Since color is associated with a single particular value, red, the plot will have only one color of marker, red. And so this is just an example that illustrates that distinction. So in the first instance, here's our aesthetic mapping, and here's our open and close parenthesis of our aesthetic mapping. So within our aesthetic mapping, we've associated color with a variable drive. There's 3 different drives, so we get these 3 different colors. Down here in this code, there's the beginning of our aesthetic mapping. There's the end of our aesthetic mapping. Outside of the aesthetic mapping, separated by a comma, we've got the association of this aesthetic color now not being associated with a variable anymore, but being given a particular value, blue, so all the markers are blue. So we've got an enormous range of colors that we can play with. You've got like bisque 1 and bisque 2, or goldenrod, or ghost white, and up here you've got a location where you can find some more information on that. I'm going to do a slight shift of topics here. I'm going to talk about this issue of overplotting. And to address that, I'm going to make a tiny little data frame called Carve2WD, which is based on MPG and is meant to contain only those records of the particular model, that the Caravan 2-wheel drive. So how would I make this particular data frame? This is a bit of a review. I'm going to start off with MPG. There's my piping operator, and then I'm going to use the filter function, and I want to retain only those models that are Caravan two-wheel drive. So I specify model, and of course the double equal sign, because what we're doing with filtration is we're requiring a logical test. So we've got this logical test here. That's the question, is model identical to this particular value? Notice that it's in quotes. So that's our first step. We filter the data, so we've only got the records associated with that particular model, Caravan two-wheel drive. We continue on with our piping operator, and then we do group by and summarize. As always, when we do group by and summarize, we're summarizing, we're compressing the data frame. How many records are we going to have? We'll have one record for each unique combination of city and highway mileage. And there are our unique combinations of city and highway mileage. Then we continue on with calculating the summary statistic. How many variables are we going to have? The only variables we're going to have are those that are either specified within the grouping function, city or highway mileage, or created by the summarize function, count, and there we go. But here you see the issue. The issue is we've got a grand total, if we add them all up, of 11 records. We add all these counts up, we've got 11 records. Excuse me, we've got 11 records, but only 7 unique combinations of city and highway mileage. So when we make our plot, each one of these records is evaluated, and the value of the record determines the city and highway values. We're only going to see 7 points, 1 point for each one of those records, even though there are actually 11 vehicles in this particular data frame. So, in a sense, this is rather a misleading plot because we're only seeing 11 points. So, how do we deal with that? One way to deal with that is to use this thing called alpha. And alpha controls the transparency of the point. And the whole idea is if the default alpha is 1, and if I were to set alpha to be equal to 0.2, then that point is going to be a much lighter shade. In fact, so light, take the 1, divide it by the 0.2, you need 5 points on top of one another to make complete blackness. So I'm going to make this plot here, and I've noticed here I've made the background white. And in the next lab, we'll talk about how to make the background white. For right now, I'm not going to bother showing that because it would be a distraction. But what we're going to do is we're going to start off with this very small data frame. And there's our aesthetic mapping. Highway mileage on the x-axis, city mileage on the y-axis. But now I've added as an option, I've specified that the transparency should be equal to 0.2. And now I can see where my 11 points are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, one question that might arise is, well, how would you even know that this was a problem? Well, one way you might know this is a problem is I would encourage you when working with your own data, if you're not really familiar with how the data is structured, you should do something that we saw in the last lab, or I think in the first lab, where we had the xtabs function, where I could use the xtabs function, operate on the data frame two-wheel drive, have highway and city mileage as my variables of interest, and we see here's city mileage, here's highway mileage, and we can see where the duplicates and the triplicates exist, and we should be aware of the fact that we could have an overplotting problem. Here's an alternative. If we come back to our data frame, Caravan two-wheel drive, we've got this variable count. What we could do is we could aesthetically map size on the count, and that's what's happening in this code here. So we specify our data frame, we want a scatter plot, and here's the opening and closing parenthesis of our aesthetic mapping. Highway mileage goes on the x-axis, city mileage on the y-axis, but now we've mapped size onto this variable count, so each one of these records is evaluated, and the size of the marker is going to be determined by the value of count. So once more, we can see our 11 records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll start. Previously, we looked at scatter plots that were produced by Geom Point. Now we're going to look at line plots produced by Geom Line. Where do we use line plots? Oftentimes we use them in situations like this, where we're looking at some variable. In this case, we've got regular gas price over time. So there we're seeing the change of gas price 2018, 2019. And looking at how a variable changes over time is one of the most common uses for a line plot. There is, however, an alternative use, and that is to look at this question of whether or not two variables are interacting. And that's something you'll see in the courses that follow on to this one. But the interaction phenomenon is an important one. And this plot was produced based on some simulated data. I made the data up assuming that there would be an old variety of plant, an agronomic plant, and a new variety of agronomic plant. They were given either one of three nitrogen treatments, NH3, none, or NO3, and kind of a hint that this is simulated data, not real data, is that in actuality I don't think that NH3 is a particularly good fertilizer. But I've shown the results of that experiment as a line plot. And the value of looking at a line plot is that when I examine this plot, what I can see is that if I look at nitrogen treatment none, that new is better than old in terms of average yield, which is my variable of interest. And similarly, if I look at NH3, new does better than old. However, the situation is reversed if I look at those crops being given NO3. In NO3, the yield is greater for the old variety than for the new variety. Why is this important? Well, it's important, for example, because with NH3, new is better than old. For NO3, old does better than new. And that means that one can't really meaningfully answer the question, in general, which one of those two varieties is better. Because which variety is better depends entirely upon the nitrogen fertilizer that's given to them. So in any event, this whole concept of interaction is an important one in interpreting results when you've got a factorial experiment where there's two factors, nitrogen in this case and variety in this case. And so when you've got an interaction such as you see here, then one cannot meaningfully speak of an overall effect of nitrogen or an overall effect of variety, because the effect of nitrogen depends on the variety and the effect of variety depends on nitrogen. And line plots like this are a good way to detect that interaction. So in terms of the coding for this new Geom line, we're going to go back to this template that we've seen several times before. And overall, the template doesn't look that different for Geom Line than it did for Geom Point. We're going to have our two layers. We're going to have the plotting function in which we specify the data. Then we're going to add with a plus sign our geom. And that geom is going to have these 5 different things, as always. And as we saw in the case of a scatter plot, really, we could get away with just this one, because the data could be inherited, the options are optional, and the stat and position defaults are just fine. And we can see that in this particular example. We've got this tiny little data frame, MPGF, and we've got year and miles per gallon. So we reference that data frame in our plotting function. Then we add as a layer with a plus sign, Geom Line. There's the open and close parenthesis of Geom Line, the open and close parenthesis of AES. The X location is mapped onto year, the Y location is mapped onto MPG, and there's the plot we get. Here we've got a slightly more complicated data set where we've got MPG, we've got year, we've got MPG, and we've also got, however, this new variable origin, so the vehicles can either be made domestically or they can be imports. So we reference this data frame MPGG, we add as a layer geom line, there's our code, and what we get is not terribly attractive. And it's not very surprising that we're getting problems. Because if we look at what's happening here, if we look at, for example, the year 2009, we get one value for the domestic vehicle and another value for the imports. We get one value for the domestic, we get another value for the imports. And similar, if we look at 2012, there's 2012, we get one value for the domestic and another value for the imports. Now, if this was a scatter plot, it wouldn't look that all weird, because you'd have a point here, and a point here, and a point here, and a point here. But this is a line plot. So as a consequence of being a line plot, all these points get connected, and you're given this sawtooth type appearance. So how are we going to solve that problem? We're going to solve that problem by the first part's going to be the same, plus sign's going to be the same, the geom line, but now look at our aesthetic mapping. There's the open and close parenthesis of the aesthetic mapping. We're going to add an additional thing to the aesthetic mapping. We're going to map group onto origin. And remember how aesthetic mapping works, is that every record is evaluated, and the value of the variable determines, in this case, the group that it's going to be in. So what we wind up with are two lines. Now we've got two separate lines because we've mapped group onto origin, and the value of origin, because it's a mapping, is going to determine what group it's in. Now, the obvious problem is we don't know which one is domestic and which one is an import. But that's easily solved. So this code is very similar to what we saw before. There's our aesthetic mapping, and it's open and close parenthesis. Year goes on the x-axis, miles per gallon on the y-axis. We group according to origin and get separate lines. But now I've added an additional mapping. I've mapped the aesthetic color onto the variable origin. So every record is evaluated, and the value of the origin is going to determine the color. So now I've got two colored lines, different colored lines, the two different origins, and a nice little legend that tells me which is which. Bit of a confession here, I really have trouble struggling with understanding this grouping function that we saw earlier. And the reason is, if one was to use this code here and operate on this data here, we would get a nice looking plot just like the one we saw in the previous slide. But note, this code here lacks the grouping function. So what appears to be happening in this block of code is that mapping color onto origin seems to have been adequate to generate these two separate lines without having to group by origin. And so the obvious question is, okay, when do you need to use group equals? When is it required and when is it not? And frankly, it's not terribly obvious to me. The good news is that in a case like this, if I had group equals origin, it wouldn't have created any problems. The other good news is, in those circumstances where grouping is needed and you fail to group, usually things blow up in a spectacular fashion and you get something that looks really weird like this guy. So the bottom line is that if you're doing a line plot, so if you're doing a line plot with geom line and you get something that looks really, really weird, then perhaps you should ask yourself, maybe I should have used group equals. Okay, geom line. So earlier on, we saw this slide. We saw that with dealing with geome point, we had these 25 different shapes. And we further showed that we could map shape onto a variable. In this case, we mapped shape on the drive, 3 different drives, and we got these 3 different shapes. Whereas geome point has shape, the analogous feature with geome line is line type. So geome point has shapes, geome line has line types, and they can either be mapped or they can be set. So in this particular case, we're mapping line type onto origin. So there's our aesthetic mapping, and there's its open, and it's closed parenthesis, and this we've all seen before. Exon takes year, MPG on the y-axis. We're grouping and coloring by origin, but now we're doing an additional mapping. We're mapping line type onto origin. So because it's a mapping, all the records are evaluated, and the value of origin is going to determine the line type. And you can see in the resultant plot that we've got 2 different line types. So this particular code illustrates the mapping of line type. Down here we've got some code that shows the setting of line type. So here's our aesthetic mapping, and it's open and closed parenthesis. And here's our geome line with its open and closed parenthesis. So this is all the aesthetic mapping. But outside the parentheses of the aesthetic mapping, followed by a comma, I've set the line type equal to 3. Now, in the previous slide, an earlier slide I should say, we saw that there are 25 different shapes available with geome point. In contrast with geome line, there's only these 6 different line types that we have available to us. So, in this case, we've set line type equal to 3. There is line type equals 3 is a dotted line. And so, as always, when we set, because we specify that line type is going to be equal to 3, there's only going to be a single line type, and that's going to be 3, which is going to be the dotted line. Switching topics slightly, what I want to do is produce a plot that looks like this, where essentially I've got a scatter plot, but now the points have been connected with lines. And so in order to produce this plot, what I'm going to do is I'm going to take advantage of the fact that ggplot2 is a layered language. And I'm going to superimpose 2 layers, one to make a scatter plot and the other to make a line plot. Now in this particular case, the data is a little simple data frame that I made up called folks. It's got 3 children at different ages. The weights were determined, and this is the plot that I want to make. So here's the code that's going to do that. So here's my plotting function. So I'm going to have a plotting function, and then I'm going to add as a layer to make a line plot, and then I'm going to add as a layer with a plus sign, a layer to make the scatter plot. So that's the overall approach I'm going to use. I'm going to take advantage of the fact that ggplot2 is a layered language. Now, let's go back to this slide that we saw quite a while ago on inheritance. And we said typically the way we do business in ggplot2 is like this. Within our plotting function, we specify the data, and then everything else goes inside our geome. But I said occasionally what we'll do is we'll put all the information inside the plotting function and have that inherited by the geome. And that's sort of what we're going to do in this example. So if we think about this mapping, the aesthetic mapping, it essentially says put age on the x-axis and weight on the y-axis. That's going to be true both for the line plot as well as for the scatter plot. Now I could have taken this and shoved it inside of the aesthetic mapping for both the line plot and the scatter plot, or, and this is what I've done here, I've saved myself some time and effort. By putting this information up here in the plotting function, it will be inherited. It'll be inherited by both the line plot and the scatter plot, and I've saved myself some typing. So, in terms of my line plot, what I'm going to do is I'm going to group by person and color by person, so each one of these individual children is going to get a different color. So that's going to be my line plot. In terms of my scatter plot that's created with GeomePoint, I'm going to have some mapping and some setting. So there's GeomePoint, and there's its open parenthesis and its closed parenthesis. Here's my aesthetic mapping. There's its open parenthesis and its closed parenthesis. And there's a comma there. I've set the shape equal to 23. So shape 23 is one of these diamond guys with some color inside. And as we saw earlier, when we've got one of these shapes that's got a separate color on the outside and a different color on the inside, the keyword color only controls the border, and the predominant color is determined by fill. That's the predominant color that's on the inside. So what I'm going to do is I'm mapping fill onto person. So every record is going to be evaluated, and the value of person is going to determine the predominant inner color. The shape is 23 is going to give me this shape. Color equals black. What color equals black is going to do, that's going to just specify the border color. And size equals 8 is going to determine the shape, or the size of the point. So here's the code. So we've got these three layers: the plotting function, geom line, and geom point, added together with a plus sign. So within the plotting function, I'm going to have the aesthetic mapping that says age goes on the x-axis, weight goes on the y-axis. That'll be inherited by both geom line and by geom point. Within geom line, I'm grouping by person. Don't know whether it's necessary, but it doesn't hurt to put it in. And I'm coloring by person. So I map color onto person. So these three different lines get three different colors corresponding to the three different children. In terms of geom point, my shape is 23. And I've set that as the shape. So all of the markers are going to have this basic shape that has an outer color, a border color that I've set to be black. So in every instance, the border color is going to be black. However, within my aesthetic mapping, there's my aesthetic mapping. I've filled on the person. Every record is going to be evaluated, and the inner color is going to be determined by the person. So with three different persons, I get three different inner colors in my scatter plot. Now I just want to go over some miscellaneous topics. I want to talk some more about inheritance, printing plots versus creating plot objects, modifying previously created plot objects, and putting a bunch of plots into a single one. Okay, so inheritance. This is the code that we just saw, and it worked just fine. So what happens is, within the plotting function, you specify the aesthetic mapping, and it's inherited by both the line plot and the scatter plot. And the point is that one can inherit. Geom line and geom point can inherit from the plotting function, but they cannot inherit from each other. So this code down here is not going to work. This code won't work. What I've done here is I've specified for geom line what the mapping is of the x and y variables. But geom point, there is no specification of the x and y mappings. Up here, because the specification of the x and y mappings occurred within geom plot, it could be inherited by the scatter plot. But this geom point, this scatter plot, can only inherit from the plotting function. It cannot inherit from another geom. And so because this scatter plot cannot inherit from another geom, it doesn't know what the x and y mappings are. doesn't know what the X and Y mappings are, and thus the thing fails. The difference between printing a plot and creating a plot object. So this code here, you type that in and hit run. In the lower right hand corner of the monitor, you'll get a nice little plot, because what this thing does, this ggplot function does, it says render a plot. Here we've got a slightly different code. I mean, the words are all the same in terms of what's highlighted here. But now what I've done is I've added an assignment operator and assigned to an object called myPlot. So what's going to happen is there will be an object created. An object will be created called myPlot. And because there's this assignment operator, what will it consist of? It will consist of everything that's to the right of the assignment operator. So this thing called myPlot, this object, will contain all the information required to make a plot. However, no plot will be rendered in the lower right-hand corner of your monitor. This object is created, but there's nothing here that's going to tell R to print the darn thing. If you want to actually see it, you have to use print and then specify the name of the object that's been created. So why is that important? Why is all this object stuff important? It's important because we can save ourselves some typing. So my goal is to produce two plots. The goal is to produce two plots. And here's one way to do it, and here's another way to do it. And I'm going to recommend that this way, that is based on the creation and modification of a plot object, is by far the more efficient. So let's look at this first way. This code produces that plot. And this is all code that we've seen before. And this code produces that plot. Now, if we compare these two blocks of code, excuse me, cat. Okay, if we compare these two blocks of code, then we can see that at the beginning, they're identical. So the plotting function is the same, and the information to make the line plots is the same. And if you look carefully at these plots, you can see, in fact, that the line plots are identical. Where they differ is in the scatter plots. So here's G on point for the first one. Here's G on point for the second one. Here we've got fill by person. Here we've got the fill set equals to yellow. We can see that we've got very different plots. Here's an alternative way to do business that'll save us some typing. I'm going to create an object called base. And base is going to consist of all this stuff here, which equals all this stuff here, which is all the stuff that these two plots have in common. So once I've created this object called base, it won't be printed. I've created it, but it won't be printed. But however, once I've got it in hand, I can then attach to it with a plus sign a layer, the layer for the scatter plot. So the combination of the base, which has the information required to make the line plot, added to it the code to make the scatter plot, is going to give us this particular plot here. On the other hand, if I start off with base and add with a line this code to make the scatter plot, then I'll get this particular plot here. So by creating this object called base that has the information that is common to both plots, then I can use that as the starting point to create these two additional plots. Just to reinforce a point that I made earlier, if this hadn't been here, then what this block of code would do would print the plot. However, because there is an assignment operator, nothing gets printed, but the object is created. if we come down here, note that there is no assignment operator. Since there is no assignment operator, then this will trigger the printing of a plot, and this will also trigger printing of a plot. So, thinking again about the idea that we can create plot objects and then modify it, these three things, these three blocks of code do exactly the same thing. And this is probably the standard way, the way we saw earlier. There's the plotting function, specifies the data frame, specifies the common aesthetic mapping, then add two layers, one for the line plot and one for the scatter plot. This is an alternative way to do business. I could create an object called base1 that had the plotting function together with the common aesthetic mapping. Now, this particular code here would not result in a plot being rendered. You wouldn't see it on the monitor, and there's two reasons for that. First reason is I've got the assignment operator. And by virtue of having the assignment operator, I'm creating this object, but nothing is going to be printed. The other reason is nothing's going to be printed would be I've got a plotting function, but remember that in order to make a plot, you need two things. You need the plotting function plus some sort of a geom. I don't have any geom, and for that reason as well, this block of code here would not result in any plot being produced. On the other hand, if I start off with this object base1 and add to it two layers, one layer to make a line plot, then with a plus sign, another layer to make a scatter plot, then in fact, because there is no assignment operator here, what would be rendered would be a combination line and scatter plot. And here's another way to accomplish the same thing. Here I start off by creating an object, a different object, an object that consists of the plotting function plus enough information to make a line plot. By virtue of the fact that I've got an assignment operator, I'm creating this object, but no plot will appear in the lower right-hand corner of the monitor. However, if I were to say print base 2, what do you think would happen? What would happen would be the printing of a very nice line plot, because there's enough information here to make a line plot. But to make the combined line and scatter plot, all I got to do is start off with base 2, that's the information for a line plot, add the information for a scatter plot to it. Because there's no assignment operator, then what would be rendered in the lower right-hand corner would be a combined line and scatter plot. Now I want to shift topics slightly, and I want to talk about how I can take these three separate plots or plot objects and combine them into a single plot. In order to do that, the first thing you're going to have to do is install and load this Grid Extra package. There's another package to think about that you might want to use if Grid Extra doesn't work for you, and that's called CalPlot. So, what I'm going to do, I'm going to begin by creating three plot objects. Base, plot 1, and plot 2. And base consists of, there's my plotting function, and there's added to it, as a layer, enough information to make a scatter plot. If I were to type in this block of code, what would I see? Well, I wouldn't see anything in the lower right-hand corner of my monitor because I've got this assignment operator. By virtue of having the assignment operator, no plot will be rendered visible on the lower right-hand corner of my monitor, but this object base will have been created. If I'd gone and done print base, then what I would see in my monitor would be a rendering of that plot. But in any event, I begin by creating this first object called base, which contains enough information to make a line plot. And then I create another object called plot 1 that begins with base and adds to it enough information to make a scatter plot. So if I were to go print plot 1, what I would get would be this plot. And then similarly, plot 2 began with base and added enough information to make a scatter plot, and that's what plot 2 would look like. So in order to combine this plot, and this plot into a single plot, I use the grid arrange function that's available with the grid extra package. So there's the grid arrange function, and it's open and closed parenthesis, and has a bunch of arguments. And I begin by putting in the plots that I want in the order that I want them to appear. Base, plot 1, and plot 2. Endcall equals 3. What does that do? It essentially creates 3 columns. So I've got 3 columns, and those 3 columns comprised of the 3 plots, base, plot 1, and plot 2.